Now, this is a very interesting example, although I have been using it for a lot of years. But it's a very interesting example because it allows us to reflect how analog differs from the digital processing. So, for example, you are asked to come up with a circuit which takes an input and divides the value by 2. So whatever the input we are getting, we want that at the output stage we get it divided by 2 or cut it in half. So obviously there are many ways of doing it, but a simple manner is to use a voltage divider circuit where we use two resistors of the same value, and we attach them with the input, and we take the output against one of the resistors. Now this, if you want to model, then this is termed as V out is equal to R over 2R V in, and obviously this makes it as V out is equal to half of V in. Now this is the analog way of doing it. So for example, you made the circuit, you burned it, you hard coded it, and then you found out that this was not y is equal to x by 2, it was y is equal to x by 3, for example. Then what you will need to do, you will need to go back and change your circuit in the hard form, in the hard way. Obviously there are other issues as well, that if you are concerned about the precision, then the values of the two resistors must be exactly same. Similarly, if you are interested in storing the data, then storing it in this form is rather difficult. So what is an alternate? Digital processing allows you an alternate mechanism which is something like this. So what in this manner, what you will have a voltage input which will first of all pass through an analog to digital converter, and then it will go into a microprocessor, and microprocessor simply knows how to run maths. Now what to do with that input is directed by a code which is stored in a memory, and somewhere in the code there will be a line V out is equal to V in divided by 2, and then the processor will run this code on the V in, and then whatever the output comes out, obviously it will be in the digital format. This goes through, if needed, it goes through a digital to analog converter, and you get the voltage output, and this output will be in the very similar form as we saw in the previous analog circuit, that this output will be half the value of whatever the input was. So this gives us a comparison of how a simple task can be done in analog or in digital. Now the advantage is obviously that after you coded everything and you remembered that it was not Vn over 2, it had to be Vn over 5, then you just need to change the code and you don't need to worry about the circuit or anything else. Similarly, the precisions and other things remain intact. Okay, so what are the advantages offered by DSP over analog signal processing? So what are the advantages? Means if a scenario comes up, then what are the features offered by DSP, so which makes it easier for you to decide whether to go for analog signal processing or a digital signal processing. So obviously, since general purpose computing platforms like controllers and computers are now available, implementing a variety of systems have become simpler and therefore inexpensive. There is a flexibility on offer as well, because modifications in programming code is only needed to change or alter the system. You do not need to make a wholesome change in the hardware. We just change the programming code to change the behavior of the system, so which makes it programmable, flexible, and inexpensive. Problems related to accuracy and precision are also better handled in DSP than in analog, because in analog there is an issue of deteriorating performance over time, which is not there in digital processing. Similarly, the devices coming for analog processing have some performance thresholds, so one device will not be 100% similar to the another similar device. So there are these issues in analog as well. So with respect to precision and accuracy, digital perform better. Lastly, data storage and encryption is in digital format is simpler than in analog. So these are some of the advantages offered by DSP over analog. However, it is not that in every domain DSP is preferred. For example, we know that in order to digitally process something, you will need computers. And if, for example, the data rates are extremely high, or the size of the data is extremely high, or very high bandwidth applications, for example, satellite high definition television application is concerned. So imagine if that sort of data or that amount of data needs to be processed through computers on a satellite, the cost of that satellite will go enormously high. So in order to address that situation, we may prefer analog signal processing on satellite. So this is just one example. There may be other cases as well. So it's not that DSP versus analog, DSP has won all the battles. These are the decisions based on the cost, flexibility, effectiveness, accuracy, data storage. These are the features on which we decide whether to go for a digital signal processing or an analog signal processing. But in most of the scenarios today, DSP performs better than analog. Okay, let us move further. Let us now look at signals in a bit deeper sense. We have already discussed earlier that a signal is a function that varies with an independent variable. Now this dependency can be single or multidimensional. For example, an electric current is a single dimensional signal which depends on only one independent variable, which in this case is time. Whereas there is an image, and we know image is a two-dimensional signal which depends on two independent variables, x and y axis. We can have a three-dimensional signal as well, such as a video signal, which depends on three independent variables, x, y, and the third is time. So we know that a video is made of a number of frames. So one frame is an image frame, which is two-dimensional, having an x and y dimension, and the third dimension is, of course, the time against which these frames move. So video is an example of a three-dimensional signal. Okay, so if we have got this understood, then let us now discuss what happens if we try and make any one or both of these axes as continuous or discrete. Again, remember that we are considering time on x-axis and the signal values on y-axis. So the first scenario is of a continuous time signal, which is defined for every value of time. This means that for every value of time, there will be a signal value present. So it means that in case a signal is defined for a time, let's say between 0 and 3, then for every value of time between 0 and 3 seconds, there will be a value of the signal present. So it cannot happen that you say that between 0 and 3 there is a point 1.111934 seconds, and at that point there is no signal value present. It will not happen. The signal will be defined for all values of time between 0 and 3. So essentially what we are saying is that there will be an infinite number of signal values between time 0 and 3 seconds. Such signals are called continuous time signals. Now the second scenario is where the signal is defined only for a certain specific values of time. The signal is not defined for all values of time. This is the difference. For example, a signal defined for a sampling period of 0.1 second